So we're going to talk about lengths of parametrically defined curves. So let C be a parametric curve. So that means it's going to be defined by x equals f of t and y equals g of t, and t will be some values between a and b. So if f prime and g prime are continuous and not zero at the same time on our closed interval, and if C is traversed exactly once as t increases from a to b, then the length of that curve C is defined by this definite integral. So we've got the integral from a to b of the square root of f prime of t squared plus g prime of t squared. Okay, so this is actually, this is similar to the arc length formula that is typically shown like when you first learn about like areas and things like that. So I want to just review an old arc length formula that we've at least talked about in my class. So typically when arc length is first introduced, so it's not parametrically, it's just that you have some f of x equation. And so I wanted to show you and review the old arc length formula. So this is the old arc length formula, which looks very similar to the one that's parametrically defined. And if you think about this, actually the parametric formula is actually just the more generalized version of this formula. And we've talked about in another video, so I'm assuming you know your parametric equations at this point. So if you wanted to parametrize some equation f of x, well, you can let your x equals t, and so the derivative of t would just be 1, so that would be 1 squared. And then you could rewrite your f of x as f of t. So this is like how you could, in general, parametrize a curve. And so you can see that this is just kind of a special case of our parametrically defined formula. And this is actually pretty straightforward to use. So we're going to just go ahead and use this. So if I want to find the length of the curve defined by x equals t squared over 2 and y equals 2t plus 1 to the 3 halves over 3, and t is between 0 and 4. Okay, so first things first, right, I know I'm going to have to take some derivatives so that I can fill in the pieces of this formula. So my x prime is just going to end up being t, and my y prime, I got to use the chain rule here. So I bring down the exponent 3 halves times 1/3, and then I subtract 1 from the exponent here, and then I multiply by the derivative of the inside function, so that's times 2. And okay, so now if I plug in what I've got, here's my x prime, here's my x prime, and then here's the derivative of my y prime, so this is what has to be squared. And so when all is said and done, this is just t squared, and then here, this 1/2 to the second, this whole exponent falls away, so I'm left with t squared plus 2t plus 1. And so in this case then, I can rewrite this formula here, t squared plus 2t plus 1. You can rewrite this as t plus 1 squared. And this is important because then thankfully we can take the square root of this. And so when I can take the square root of this, then I can actually integrate this. So if I take the square root of this, the one thing I want to mention, so a lot of people forget this. So in general, when you're taking the square root of something squared, this is just like how this works. You have to put absolute value around it, and then you kind of have to just deal with it. So in this case, I have to start by putting absolute value around my t plus 1. And then I just have to think about, okay, so what do I do with the absolute value in this case? And in this case, since my integral is between 0 and 4, all of these values are positive for t plus 1 anyways. So this is all on the positive side of how my absolute value function works. So since everything's positive, I can just I can drop the absolute value and just leave it as all positive. But you do have to do that analysis before you just go dropping the absolute value. So just an FYI with that. Sometimes that can be a sticking point in some integrals. Okay, so anyways, so now I've got this integral, super easy peasy, right? So this is just going to integrate as 1/2 t squared plus t, and then we just plug in our limits of integration, and so ultimately I'll get 12. So that's all I wanted to talk about with that particular formula. So I'm going to leave it at that, and I will talk to you guys in another one. Bye!